This is the presentation for a stoichiometry tutorial, which will help you walk through the stoichiometry reading worksheet called Predicting Amounts and Reactions. In addition, it also walks through the practice problems that would have been gone over in class. So according to the Predicting Amounts and Reactions sheet, basically stoichiometry is nothing more than a mathematical process of determining how much product is made or how much reactant is needed in a reaction. By knowing that we can compare moles of one type of material to moles of another type of material, because moles is a representation of the number of particles and does not take the mass or the size of the actual particle into consideration, we can use this technique of stoichiometry to move between different types of materials within a chemical reaction. So we have to remember that a balanced chemical reaction is going to tell us two things: which substances are involved and what the ratio of all the different particles involved is. That's why we balance it. We can make all kinds of different ratios from a chemical reaction. We're going to use a technique called a before, change, after table to organize our information and provide us with a starting point to determine what this stoichiometry of the reaction actually is. So this is the sample problem that is given in the Predicting Amounts and Reactions, the stoichiometry reading. And how I have it set up here is that I have the first thing that you're going to always need to do is write the equation. Now the equation on your sheet has been done, but I can interpret what's going on here. First off, it says hydrogen sulfide gas. So hydrogen sulfide gas is H2S, and we're going to put our state in there. And then it says that it smells like rotten eggs, so just some extra information. And it says burns in air. So burns in air we know means that we're adding oxygen gas. And then it says produce sulfur dioxide, which has a formula of SO2, also a gas. And finally H2O, good old water. And I'm running out of room. Move our screen over a little bit. Okay, so the next thing we're going to need to do is balance it. So to balance this one, we're going to need a 2 in front of the hydrogen sulfide. We're going to need a 2 in front of the SO2. We're going to need a 2 in front of the water, and then finally a 3 in front of the oxygen. So this is the ratios that's involved. And I can compare any one of these materials to one of the other materials. So I can say that for every 2 moles of H2S that's used, we're going to produce 2 moles of water. I could also say that for every 2 moles of H2S, 2 moles of SO2 is going to be produced. Or for every 2 moles of H2S that's being used, I'm going to need 3 moles of oxygen for the reaction. And I can do this for any of these. And I can also go back the other direction. So I can say also, for every 2 moles of SO2 produced, I'm going to need 2 moles of H2S. So in the before line, we want to put in the values in moles, and only moles, of each of the materials before the reaction has occurred. So before the reaction has occurred, we don't have any SO2 and we don't have any water because we don't have products yet. The reaction hasn't occurred. For the next one, we can put in, it says how many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide. So we know that we have 2.4 moles of hydrogen sulfide. Now it doesn't tell us how much oxygen we have. If you're not given a value for one of your reactants, you can just assume that you have more than enough. And this note is right after step 2 in your reading worksheet. So if we have more than enough, we can actually just say we have that reactant in excess. Now the change line is what is occurring during the reaction. How much of the reactants are being used, how much of the products are being produced. So because we're doing this reaction, we're going to use up all of our H2S. It asked us how many moles of oxygen gas we need to completely burn the 2.4 moles. So we're going to use up that whole 2.4 moles. Now using ratios, we can figure out what the other things are. So I'm going to go down to the scratch paste that I made at the bottom. And basically I can just use the ratio of the of each of the particles to determine what values are going to be in my change line. So if I want to find out my oxygen, I know I have 2.4 moles of H2S. I know that for every 2 moles of H2S that I am burning, I'm going to need 3 moles of O2. And those values I got right out of the reaction itself. And when I calculate this, I find that I have 3.6 moles of O2 needed. So that value will go there. Now if you notice, I made both of the reactants negative. That's because we're using up reactants. Now I'm going to move over to the product side, and because products are being produced, products are going to be positive values. Now for these, I can just kind of look at the ratios here. I have for every 2 of these, I have 2 of these. So 2 to 2 is the same as a 1 to 1. So if I am using up 2.4 moles of H2S, that must mean that I'm going to be producing 2.4 moles of SO2. And I'm also going to produce 2.4 moles of H2O. The after line is basically your checks and balances for your mathematics. So I'm using up all my H2S. I have a lot of oxygen. I'm using up 3.6, which means I'm going to have a lot left over. Nothing plus 2.4 is going to give me 2.4. And then finally 2.4. And actually this line should have went all the way across. There we go. Okay, so now I can go back to my question. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? And my answer to the question lies right there. 3.6 moles. Now, we're eventually going to be adding in a few other pieces, which doesn't seem like it should be, once we get this method down, a whole lot more difficult. So what if instead I asked for, say, oxygen, instead of oxygen gas in moles, what if I would have asked for it in grams? Well, now the transition's easy. Now you just have to go back to what we had done in unit, I believe, 5, where we would just take the 3.6 moles of O2, and we would use the molar mass of oxygen gas, which is 32. Oops, apologize, I am in the wrong spot. So for every 1 mole of O2, it has a molar mass of 32 grams. So therefore, I would end up having 115 grams of oxygen. And that's really all there is to doing these. It's more or less just laying it out and organizing your information so you can see everything that's going on. Now this may seem tedious and time-consuming, but trust me, it's well worth the time. Because later on we're going to be doing limiting reactants, and it's going to be really important to be able to see the ratios to determine which of your reactants is actually causing a reaction to stop. Sometimes it's not as obvious as one might think. Let's take a look at another problem here. Okay, so once again, same process. So how many moles of hydrogen gas will be produced if 2.5 moles of calcium hydride reacts with water? Now this one I left a little open-ended because I want you to start to think about what kind of reaction it is and what type of products would you expect. Now for this one I gave everybody a hint in class. I said make sure that you think about writing water as HOH and not H2O. So the first thing we're going to do is we're going to write calcium hydride. Calcium is in the second row, or a second group, which means it has a +2 charge. Hydride is a hydrogen ion, which has a -1 charge in this case. So I'm going to need 2 hydrogens for every 1 calcium. So my formula for that is going to be CaH2. And that's going to start out as a solid. And we're going to react it with water. Now in this case, I'm going to write it as HOH. Like I said, sometimes it becomes very handy to determine what kind of reaction it actually is. So calcium hydride reacts with water, and we know, based on the problem, it says it's going to produce hydrogen gas. And then we have to decide what else is left over. Well, if we notice something, this is very similar to having an A plus a B plus that's being reacted with something that's a C, which is just the hydrogen, and then a D, which is this hydroxide group. So this is nothing more than a double replacement reaction. So calcium is going to go with the hydroxide group, and then my hydrogens are going to come together. The hydrogens come together to make hydrogen gas, and then what's left over is the calcium and the hydroxide. Calcium having a +2 charge, hydroxide having a -1, so my formula at the end is CaOH2. And it's an aqueous in this case. I'm going to extend my line across right away. So now we have to balance, and it appears that all we're going to actually need is a 2 in that position and a 2 in that position. So now we're going to fill out our before line. So our before line is how many moles of hydrogen gas will be produced if 2.5 moles of calcium hydride reacts. So we're starting with 2.5 moles of calcium hydride. It's not giving us our water, so we're assuming we have more than enough. And we have no products before the reaction occurs. In the change line, we're going to be using up our 2.5 moles. We can figure out that, and we can either do the math, or we can reason our way through it, that according to the reaction here, for every 1 calcium hydride, I'm going to need 2 moles of water. Basically, I'm using twice as much water as I am calcium hydride. So if I'm using 2.5 moles of calcium hydride and I need twice as much water, that must mean that I'm going to be using up 5 moles of water. Once again, using that same kind of reasoning process, since these numbers are actually quite easy to use, I go from 1 to 2. So once again, I'm going to have 5 moles of hydrogen gas created. And now I have a 1-to-1 ratio for these two. So for every 2.5 moles I put in, I'm going to get 2.5 moles of calcium hydroxide out. Do my afterline. And now I can go back to my question. How many moles of hydrogen gas will be produced if 2.5 moles of calcium hydride reacts? And my answer is right there. That's how much is being produced. Now you might be asking yourself, why am I not picking the answers from the afterline? Well, in this case, every time we've done the reaction, I've said that we don't have any of your starting materials. But in real life, it's entirely possible that you could have some quantity of a starting material. Say, for example, a combustion reaction. In the air, there's normally carbon dioxide gas, so you are starting with a certain amount of carbon dioxide gas in the air. So it's something to consider that we need to understand where we're taking the answer from, and does it make sense? Because we're always being asked about how much will be produced or how much will be created during this reaction or how much is being used up, we can always take that from the change line. If we're asking for what is total that's left at the end, we need to consider that that's going to end up coming from our afterline. Just small semantics that we want to just be aware of moving forward. Okay, so on to the final problem. And I apologize, these should be subscript 6s. when I imported this, it didn't make them subscripts. Alright, so let's take a look at this. So how many moles of water will be produced if 0.45 moles of oxygen reacts with benzene? So this one has C6H6, so that's our first thing we're going to write. And benzene is actually a fairly large molecule. Not huge, but fairly large, so that turns out benzene's actually a liquid. And it says it's reacting with oxygen gas. Now you should be asking yourself right away, what kind of reaction is this? And it should look very familiar. We're adding oxygen gas to something that has carbon and hydrogen, so this is a combustion reaction. And the two products that are always the products of a combustion reaction with a hydrocarbon is CO2 and H2O. Now you might be thinking, why am I putting this as a gas? Remember that all combustion reactions are exothermic, so therefore if it's giving off energy, the likelihood of your water being liquid at this point is probably pretty slim. If you have it as liquid, it's not the end of the world. Let's balance our chemical reaction here. Oops. Not counting. So we're going to need a 2 there. We're going to need a 6 there. And we're going to need a 12 here. And hopefully I didn't mess up. So that's 24, that's 30, so this will be a 15. Okay, so now let's fill out our before line. So it says how many moles of water will be produced if 0.45 moles of oxygen reacts with benzene. So we're assuming that we have lots of benzene. Once again, it's not giving us anything, so we can assume that our products to begin with are 0. And now we can move on to our change line. Now these numbers are starting to get a little bit more difficult to work with, so remember you can always have a little scratch area to do the problem with. So in this case we're starting with 0.45 moles of the oxygen. Based on the reaction, I know for every 15 moles of oxygen, I'm going to need 2 moles of benzene. So when I do the calculation, when we do this calculation, we end up with 0.060 moles of benzene. 0.06, sorry, moles of benzene is being used up. I'm going to use up all 0.45 moles of my oxygen. And now I need to create my products. So once again, 0.45 moles of O2 and so 15 moles of O2, 12 moles of CO2, and that gives me 0.36 moles of CO2, 0.36, we're gaining those, and then finally my water. Now keep in mind that you can do ratios of everything, so for this one I'm actually going to do this one in my head. I'm going to compare what the value that I calculated for my benzene, which has a 2 to 6 ratio, so I know that there's 3 times as many water molecules made for benzenes that are used up, so I can just take this and do this in my head or in my calculator and just multiply this one by 3. So what I end up with is 0.18 moles of my H2O being made. I'll do my final line. Now I'll go back to my problem. How many moles of water will be produced if 0.45 moles of oxygen reacts with benzene? And my answer is right there. So now you can move on to worksheet 1. Remember that you can make all these different comparisons, so even if the problem says this much was produced, how much did you start with, you can use the exact same techniques. It's just that you're going to know how much is being produced, you're going to know this information down in this corner, and you're going to have to figure out what goes up in this upper corner. So move on to worksheet 1, and then check in for answer keys.